Welcome to this last lecture for Chapter 2 on the AICE Chemistry lecture series. We're going to be going over Section 6 today, which is going to focus on the patterns in ionization energies in the periodic table. Now, this section, we've talked about ionization energies before, and we talked about all the different factors that affect ionization energies. So this section is a bit of a review. Now, before we get into this, I want you to understand that it's not just ionization energy that is affected by the factors we're going to discuss in this section, but really anything having to do with the atom. Ionization energy, atom size, ionic size, electronegativity, electron affinity, all of those different properties of the atom can all be explained by the same basic principles that ionization energy can. So we're going to talk about this around the light of ionization energy, but always keep in mind that we can expand that, and critical thinking will be applied in the test to expand it to other parts of the curriculum, such as atomic radius, ionic radius, etc., etc. So let's discuss the patterns in ionization energy. Now, we've already discussed the 5 patterns individually, but let's put them all together so we can be concise and we can have a better idea of what we're looking at. So the first thing that we discussed was that as you move across a period from, let's say, lithium all the way to neon, or from potassium all the way to argon, the ionization energy is generally going to increase. Now, there are exceptions to this pattern, and we will discuss the exceptions. But as a trend, as a generalization, as a general pattern, as we move from left to right, we can see this in lithium to neon, for example. Those ionization energy numbers, especially the first ionization energy, is going to increase. Second, as you go from the last element of one period to the first element of the next, there's a rapid decrease in ionization energy. And this is not something that we directly discussed, but it's something that makes sense if you think about it. As we go, for example, from lithium all the way up to neon, there is a general increase in ionization energy. What this next section is saying is that as we go from neon to sodium, to the first element in the next period, we're going to get a huge decrease in ionization energy, which makes sense because as we were going from left to right, the ionization energy increases. But then as we go down to the next period, then that's going to have a rapid decrease because of the addition of that new layer. And again, we're going to discuss the factors specifically as we go through this section. Number 3, as you go from beryllium to boron, so as you go from group, and realistically speaking, this is actually a more general or generic trend or exception. As we go from beryllium to boron, from group 12, from group 2 to group 13, from beryllium, which is in group 2, to group 13, we're going to get a slight decrease in ionization energy. So this is not a trend, this is an exception. The trend was, number 1 here, that as we go from left to right, it generally increases the first ionization energy. But as we go from beryllium to boron, instead of getting that increase that we would expect, we have a slight decrease. Again, we'll figure out why later on, or we'll talk about why later on. But for now, just know that there is a decrease from beryllium to boron, or more specifically, which will probably serve you better, from group 2 to group 13, that there is a small decrease. Next, we have that as you go from nitrogen to oxygen, so this is another exception, or better put, from group 15 to group 16. From nitrogen to oxygen, or from group 15 to group 16, I did not write that right. There is going to be a slight decrease again in ionization energy. So essentially, we have 2 exceptions. We have, as we go from left to right, the ionization energy is going to increase, but there's an exception from beryllium to boron, or better put, group 2 to group 13. And then there's another exception from nitrogen to oxygen, or better put, from group 15 to group 16. Again, we're not going to discuss the why yet, although we'll get to that. But just know that these are the two exceptions that happen in the period trend of ionization energies increasing across a period. Finally, the last trend is that as you go from the top of a group to the bottom of a group, so something like hydrogen to francium, as we go down a group, the first ionization energy of the elements are going to decrease as you go from top to bottom. So actually, let me put this in a different color. As we go from hydrogen to francium or down any group, that ionization energy is going to decrease. So those are the 5 kind of trends and exceptions that you are going to be looking at. Left to right, it increases. Top to bottom, it decreases. For ionization energy, there's an exception between beryllium and boron, or group 2 and 13, that where it decreases slightly. There's an exception between nitrogen and oxygen, or group 15 to 16, where it decreases slightly. And as you go from the end of one period to the beginning of the next, there's a large decrease. So now that we know that those are the 5 patterns, let's discuss why each of these patterns happens. Now again, some of these we're going to do very briefly because we have already talked about them. Some of them we're going to spend a little more time on. So number 1, as you move across a period, ionization energy generally increases. This is what we discussed back in the beginning of the chapter. The nuclear charge, as we go across a period from left to right, the nuclear charge increases. Remember, nuclear charge is how positive the nucleus is, or we can see it as the number of protons. So as we go from left to right, the number of protons increases, and so does the positive nuclear charge. The distance between the outer electrons and the nucleus, though, remains relatively constant. We're going to say it remains constant. It does change a little, as we saw with atomic radius, but it is very slight amount, so we're going to say relatively constant. And then the shielding remains constant because there's no new inner energy levels. We're working always within the same energy level whenever we are working in a group. In a period. So whenever we're in the same period, we are working with the same energy level, which means that the distance does not change greatly. The shielding does not change greatly. So the only things really affecting, the ionization energy is going to be the proton charge or the nuclear charge, the number of protons. And so the more protons we have, the larger the charge. And then we always justify this by saying more attraction. So there's more attraction between the electrons and the protons, or the nucleus, and that larger attraction causes the larger first ionization energy. We always want to bring this back to attraction. When we're discussing this in the AICE exam, we always want to bring it back to attraction. There's more attraction between the electrons and the larger number of protons, and therefore the ionization energy increases. Next. As you go from the last element of one period to the first element of the next period, there is a rapid decrease in ionization energy. And again, same 3 factors we're going to be looking at. Number 1, the distance between the outer electrons and the nucleus increases. This is very important. Why? As we go from one period to the next, we have now a new energy level. Ooh, that is an ugly E. Let's fix that. Now we have a new energy level. Because we have a new energy level, the distance between the outer electrons and the nucleus is going to increase because that energy level adds distance. The shielding is going to increase because that energy level, again, adds shielding because now we have a new inner energy level. And finally, the nuclear charge increases, but again, it is outweighed by the other factors. So nuclear charge here is going to increase. We're going to get more protons, which normally would lead to a bigger ionization energy. However, And we always want to say this, it is outweighed by shielding and distance. And the distance. Those two other factors are going to be more significant than the increased number of protons. And so what does this all boil down to? Again, we want to bring this back to attraction. Because we have more shielding, which prevents nuclear charge, so it's less effective nuclear charge. Because we have more distance, which weakens the attraction, we're going to have overall less attraction between those valence electrons and the protons in the nucleus. Because there's less attraction, that means it takes less energy to remove them, and therefore our weaker or smaller first ionization energy. So that's number 2. Number 3. As you go from beryllium to boron, there is a slight decrease in ionization energy. Now, this is the exception, right? Because from beryllium to boron, going left to right across a period, we would expect more or an increase in ionization energy. But we don't. We get a decrease from beryllium to boron. Again, from group 2 to group 13, because we skip over the transition metals. From group 2 to 13, we have a slight decrease instead of an increase. Now, this is because the distance between the outer electrons and the nucleus increases slightly because of the p sublevel. The electron configuration for group 2 is going to have S2 with 2 electrons in the S sublevel of whatever energy level we're currently on. In the case of beryllium and boron, it will be the second energy level. With group 13, we're now going to have that S2 P1. We have introduced the P sublevel or subshell. Now again, if we're doing beryllium and boron, but this can be with anything, so I don't want you to be stuck on this, but if we're doing beryllium and boron, this will be 2s, and then this will be 2s, 2p. If we were doing the next period down, it would be 3s2, 3s2, 3p1. But the important part here is that we're introducing the p sublevel. When we introduce the p sublevel is slightly bigger than the s sublevel we had before. Think of the shapes of the energy levels, right? If we have that s sublevel, which is a sphere, and then we, on top of that, add the p sublevel, which are those dumbbell shapes. The dumbbell shapes are bigger by this amount than the sphere is. And so we have a bigger sublevel. So when we introduce a p sublevel, we are introducing a bit of distance. And that distance is going to help drive down the ionization energy. The shielding increases slightly. Again, this is not shielding. So even though we can call it shielding, I'm going to reintroduce this as only for energy levels and say the repulsion. The repulsion increases slightly. Again, we can use the word shielding, and some of the textbooks, I believe your textbook does, but I prefer the word repulsion because shielding refers more to shielding between energy levels. Here, it's more of a pseudo-shielding between sublevels. So we're going to call this repulsion instead of shielding. So repulsion increases slightly. Again, because now we have p sublevels that are bigger than the s sublevel, and those p sublevels are going to have a fair bit of repulsion with those s sublevels. Between the repulsion and the p sublevel, both of these indicate a decrease in energy level. And now finally, the nuclear charge does increase, but it is outweighed by the other two factors because it's only an increase of 1 proton. We get 1 extra proton from group 2 to group 13, and that 1 extra proton is not enough to outweigh these 2 other factors that happen. And that's where our exception to the trend between group 2 and 13 comes from. The fact that we have a larger distance and a bit more repulsion from the introduction of the p sublevel to the new element. and that those two factors, a slight bit of repulsion that it adds the piece of level and the slight bit of distance that the piece of level adds, are going to be outweighing that inclusion of one new extra proton. So that's third. Let's look at the fourth. The fourth is the other exception. So the fourth is the exception that happens between nitrogen and oxygen, or better put, group 15 and group 16. So from group 15 to 16, again, across a periodic table or across the periods, we would expect an increase in first ionization energy. But between groups 15 and 16, we see a slight decrease in ionization energy. So again, this is an exception. Now, why does this exception happen? Because of something we discussed earlier, which is spin pair repulsion. This is because spin pair repulsion adds an extra amount of repulsion on the element that does not want to be there. So in order to look at this better, we can look at the box notation for nitrogen and oxygen. Now for nitrogen, I'm going to put it in different colors. I'll put it up here. For nitrogen, the box notation will be 1s, 2s, 2p. And that 2p has three orbitals, each of which has 1, 2, 3 electrons in it. So we have 3 electrons in that 2p or a sublevel for nitrogen. So there is no spin pair repulsion here. Now, if we look at oxygen, on the other hand, oxygen has 1 more electron. And again, these are representatives of group 16 for oxygen and group 15 for nitrogen. This is going to happen between these two groups regardless. But we'll take nitrogen and oxygen as an example. When we have oxygen, we have 1s with its 2 electrons, 2s with its 2 electrons, and then the 2p sublevel is where the issue happens. We have the 2p sublevel with 3 orbitals, and there are 4 electrons in the p sublevel of oxygen. That means 1, 2, 3, and then the 4th electron is paired up. That means that oxygen has spin pair repulsion. Also sometimes called electron pair repulsion. But because of these 2 electrons right here for oxygen, let me use a different color. Because of these 2 electrons right here for oxygen, that is not good. These 2 electrons are causing spin pair repulsion to happen for oxygen, which means that those 2 electrons don't want to be there. They're being repelled by each other. It's necessary because there's nowhere else for that electron to go. But because of spin pair repulsion causing more repulsion, extra repulsion, added repulsion between the electrons, that means that that electron becomes easier to remove. More repulsion means less attraction for the nucleus, and that means easier to remove, meaning lower energy or lower ionization energy. And so spin pair repulsion is what causes the trend exception that we have between groups 15 and 16 on the periodic table between nitrogen and oxygen. And you should be able to explain this in an AS exam using the word either spin pair repulsion or electron pair repulsion or electron spin repulsion, something along those lines. Finally, number 5. As we go down the group, the ionization energy of the elements decreases. And we have already discussed this one pretty well. The distance between the outer electrons and nucleus is going to increase as we go from one period to the next. We are adding energy levels. That increases shielding as well. Now, both of these factors, both the increased distance that is caused by the new energy level and the new shielding that's caused by the new energy level are going to cause less attraction of the outer electrons or the valence electrons for the nucleus. And so these are going to outweigh the increase in nuclear charge. So we do have more protons in these elements because we're in a whole new group. That means we have added a whole new energy level protons. But that is outweighed by the shielding and the distance. The shielding and the distance means less attractions of the electrons, more specifically the valence electrons, to the protons in the nucleus. And so that lower attraction means that our ionization energy is going to decrease as we go from top to bottom. Again, so shielding and distance are increased as we go down the group because of added energy levels. Those outweigh the increase in number of protons and in nuclear charge. And so the lower attraction means that the electrons are less attracted to the proton. And so the ionization energy is going to decrease. So that's the fifth and final one. So let's look at a few examples that we see here. So here we see how we can use successive ionization energies, which we discussed back in section, I think, 2, to kind of talk about the electron configuration of an element. So we're putting the ideas from the previous section where we talked about ionization energy and the current section where we talked, or actually one of the other previous sections where we talked about ionization energy and electronic configuration and putting those together. So here it says the 5th to 8th ionization energies of 3 elements in a third period of the periodic table are given. The symbols used for reference are not the actual symbols for the element. That just means something along the lines of Y does not mean deuterium. It just means Y, like some random element, X, Y, Z. And they give us this 5th, 6th, 7th, and 8th ionization energy. And here it says complete the electronic configuration of element Z. So first things first, we are looking at element Z. So we don't care about X, we don't care about Y. We can block those off because those are not the elements that we're looking for. So I'm going to put a line through them so we don't look at them. So we're not looking for X, we're not looking for Y, we're looking for Z. And it's important to block out data that we don't currently need. As you can see, this is part 4 of Z in a question. This other data, Y and X, were probably used for other parts of this question. But if we're not answering a part about that particular or those particular data, then we just need to ignore it. Because it's going to be easy to get caught up into looking at things that we shouldn't be. Now, we are going to look at the transitions for Z between energy levels. You have the transition from 5th to 6, 6 to 7, and 7 to 8. If we take a quick look at these, we can see that from 5th to 6, we have roughly 3K in change. 6,000 to 9,000, again, we're not looking super detailed, just roughly 3,000 difference. You do not want to sit there and waste time actually trying to figure out the actual difference because this is not what this electron job or first ionization energies, ionization energies are about. We have a jump of 3K. The next, from 6 to 7, from 9,000 to 11,000, we have a jump of roughly 2K. Remember, we're looking at where the biggest jump is between these successive ionization energies. So these are fairly equivalent to each other. Now, from the 7th to the 8th, we have a jump of roughly 22,000, or 3 times bigger. That is a big jump that we usually look for that tell us the number of valence electrons in an element. So here between the 7th and the 8th is where we see that big jump. Because the big jump is between the 7th and the 8th, we're going to look below that, meaning that this element Z has 7 valence electrons in it. Now, normally, this will not be enough data to do an electron configuration. Why? What that tells us is that the very last energy level, whatever it may be, of this element has 7 valence electrons. Another way we can view this is as this is an element in group 17, meaning halogen. Because if you have 7 valence electrons, remember the valence electrons are tied to the group number. So this has to be one of the halogens, either fluorine, chlorine, bromine, iodine, or astatine. Well, that doesn't tell us much, right? Because if we need to do the electron configuration for this element, we have 5 different choices. How are we supposed to know which it is? And that's where critical thinking and reading our questions properly comes in. If we reread this question, the 5th to 8th ionization energies of 3 elements in the 3rd period of the periodic table are given. The symbol used for reference are not the actual symbol of the elements. Well, they gave us the rest of the information that we needed. Because this is an element in the 3rd period, we have narrowed it down to the halogens because it has 7 valence electrons. Well, there's only one halogen in the 3rd period. Fluorine in period 2, chlorine in period 3, bromine 4, iodine 5, astatine 6. There is no period 1 halogen because there's only 2 elements in period 1. So that means if this is period 3, so it has to be in period 3 and it has to be one of the halogens, then that means that we're doing the electron configuration for chlorine. And so all we have to do now the question becomes a lot easier once we know that it's not all of this, is what is the electron configuration of chlorine. The electron configuration of chlorine would just be 1s2, 2s2, 2p6, 3s2, 3p5. And that's where that 7 is, right? We have our valence shell is the 3rd energy level. We have 2 electrons coming from the S, 5 coming from the P. That's 7 valence electrons in total. And so this is the electron configuration for element Z, which just so happens to be chlorine. Now we check our answer key. That is exactly what we have. Now this is only one point. It is a high-level critical thinking question, or not high level, but a critical thinking question. But it is one where we have to put what they give us along with our knowledge to kind of solve the puzzle. Now, this should not take too long because, like I said, electron configuration should be a basic skill that you're carrying over from honors chemistry. The critical thinking aspect of this question and knowing how to read successive ionization energies, that's the part of this question that comes from the AS curriculum, not just knowing how to do an electron configuration. So let's look at, like we said, there is our answer. And notice it has the 1s2 in the front here. So we cannot do a noble gas abbreviation for this question. All right. We have to do a full electron configuration. Now let's look at one more question before we finish up this chapter. If we look at this paper 2 question, explain why the first ionization energy of neon is greater than that of fluorine. So here we're being asked to compare 2 ionization energies. That of neon, the first ionization energy, that of neon and fluorine. I want to direct your attention to the fact that this question is 2 points, 2 marks. So there's a few things to consider here. One is the comparison, right? Explain why the first ionization energy of neon is greater than that of fluorine. They're already telling us it's greater, so you're not going to get a point here for stating that. What you will get points for is the different levels within the explanation. So first of all, let's look at the periodic table to see where neon and fluorine are. Where do they fall on the periodic table? So if we bring up the periodic table, we're comparing here neon and fluorine. So we're comparing fluorine, which is right here, element number 9, and neon, which is element number 10. So we are comparing 2 elements in the same group of the periodic table. So same group. That's right. Oh, let me not use yellow. So I'm going to put here same group, Fluorine is 9 and neon is 10. So they're right next to each other. Now, taking this back, let me remove the periodic table. And again, neon and fluorine right next to each other in the same period. Ooh, I put group. Same period. Let's not make that mistake. So these are the same period of the periodic table. These are both in period 2. And fluorine is number 9, neon is number 10. So once we figure that out, all we have to do is bring back the knowledge that we have from the comparison of the trends. So we know that as we go from left to right across a period, that the ionization energy is going to increase. And that is what they're telling us. Neon is greater than fluorine. So that checks out. Now we have to remember the reasons why. So what were the reasons why the ionization energy increased? Number 1. I'm going to write them right here. Oh, that's a little too small. Number 1. We know that we have a larger number of protons. So that means a larger positive charge. We know that, number 2, shielding and size stay the same, relatively. So from neon to fluorine, or from fluorine to neon, should I say, the shielding doesn't really change, the size doesn't really change. They're in the same period. There's no extra energy levels. We can say also same energy level. And then finally, we have to talk about attraction. Electrons, or valence electrons, let's put it that way, are more attracted to the nucleus. The electrons are more attracted to the nucleus because of that increase in nuclear charge. So they have a large number of protons, shielding and size stay relatively the same, so the valence electrons are more attracted to the nucleus, which means, and then we wrap it all together, that more energy is needed for the element on the right side of the periodic table. For, say in this case, neon than fluorine to remove electrons. And that's basically the information that we have, right? This is everything we have. Now, the only thing that we have left to do is put it into words. So in order to do this, and I'm not going to type it out, but you could say something along the lines of, there's a larger number of protons in neon than fluorine, because again, this is a comparison question or an explanation question. You need to address both things. There's a larger number of protons in neon than in fluorine. They both have the same shielding and size, relatively speaking. And so the valence electrons in neon are more attracted to the nucleus because of the greater charge. And so more energy is needed to remove the electrons from neon than fluorine. Now, notice, it's only 2 lines and there's only 2 points. Do we need every single piece of that? Probably not. But if you are unsure of which pieces you need, because the question is very basic in this case, you want to put more rather than less. You just want to do it in a way that is very concise and does not require you to speak too much of or to write too much. And here we have it. Greater nuclear charge means a greater number of protons, and then same shielding, same number of electrons. We didn't need to as far as the attraction, but if we did, it will be fine because we had already stated the shielding and the number of protons. And that is it. That is the last slide for chapter 2. We'll discuss chapter 3 in the next video and we'll move on from there. Thank you for joining us for our AICE Chemistry lecture.